Okay, today we have Eva Belmont, who's going to tell us about applications of Guozhou and Wang's minimal resolution ext resolver to the p=3 Adamsnovokov spectral sequence.
All right, yeah, thanks for the invitation. So I'm going to say that this talk is going to be a little bit different from, I think, all of the ones that we've had so far in the seminar, because I'm not the original author of the software being discussed. So this talk is going to have a bit of a different perspective. So I'm talking about Guozhou and Wang's ext resolver, and my experience with it is I've modified the code to do some slightly different things, and I've also used it in some Adamsnovokov computations. So I'm giving a bit of a user perspective and sort of a light programmer perspective, maybe. So the plan for the talk is there are two main sections. First, since Guozhou's program, I think, hasn't been given significant airtime in this seminar, I thought I would give an introduction to what the program is and sort of the main features of what does it do, a little bit about the mathematical strategies there. And then the second part of the talk, I'm going to talk about my work using it. So I used it to compute the Adamsnovokov E2 term at the prime 3. And there's sort of some fun things you can do there that I claim are much easier given computer computations. Yeah, and if there's time at the end, I might share a little bit about my workflow for how I use the output of his program, but we'll see how things go. All right, so I'm going to start by talking about Wang's code. So first, just a little bit of history. I believe that this was written for the original purposes were first some lambda algebra calculations for our the algebraic Atiyah-Hirzebruch spectral sequence for RP infinity, and then maybe one of the more famous uses of this was computing the algebraic Novikov spectral sequence at p=2. So that algebraic Novikov spectral sequence, one way of saying it is that it filters BP star BP by the ideal I of all of the VNs. So that's at p=2, that's just some spectral sequence that computes the Adamsnovokov E2 term. At odd primes, it turns out that E2 page of the algebraic Novikov spectral sequence actually coincides with ext over the Steenrod algebra. So I was more interested in this at odd primes, and so this actually gives you a spectral sequence from ext over A to ext over BP star BP. So Guozhou was interested in this because their connections to the C-motivic story, computing the algebraic Novikov spectral sequence gives you some C-motivic differentials, namely the ones that are seen by the cofiber of tau. Okay, and in the original code, there's also a bunch of stuff about directly computing C-motivic Adams E2 terms. Okay, and so I'll briefly say I was interested in this in two different projects. One of them is sort of still in progress. So first, I just adapted Guozhou's program to work at p=3 as opposed to p=2. So, I'm not trying to sell that as like a major change. It's not a major change. This should be thought of as within the realm of things that the program does with, some amount of effort on the other end. And so there are a couple of p=3 projects that I was interested in. I also did this a little bit for other odd primes, and I think never really did anything with it, but that's also a thing one can do with this. And also this is something that I've been working on off and on, is doing the R-motivic Adams E2 term. So yeah, hopefully that would simplify some computations in Dan and my work. Okay, so a little bit of an overview of this program. So I wrote here minimal resolution, minimal star. So the star I'll talk about in more detail later. The point is that you can lift other resolutions. So I'll say more about that. In terms of how general this is actually very general. So the core code works for computing ext over an arbitrary Hopf algebroid. And I'll say sort of the caveats here are, well, the more different the example is that you're interested in from the ones that Gaussian has already done, of course, the more work is required. And you do have to actually modify the program and write C++ code to make it do anything other than the original intentions. So for example, how does this, so it's like, okay, if you want to do it for some other kind of Hopf algebroid, you have to specify as a program, what does that Hopf algebroid do? Like, what's the ring structure? What's the coproduct? And there's also some stuff I'll get into a little bit later about you have to define some filtrations on some things. So, as an example, what does BP star BP look like from the perspective of code? So, for example, you're going to view the monomials. So, what are the elements in BP star? It's a polynomial algebra. So there is kind of a built-in way of thinking about polynomial algebras as, polynomial algebras even in infinitely many generators. So you've got elements like this in BP star, and you're thinking of them as sort of tuples of exponents, and really it should be thought of as like hashes of tuples of exponents, kind of. There's
Eva, are you writing something? I think we're seeing your facts and features slide, but I don't know if we're seeing any.
Really, that's okay. I don't know. Can you not see? So after the line structure of A gamma.
Yeah, I mean, you were writing the monomials, right?
Yeah.
Oh, okay.
Yeah,
okay.
so we could see. Yeah.
Okay. Yeah. Okay. So we're thinking of monomials in a polynomial algebra with infinitely many generators. So this is sort of, one of the built-in notions where if your Hopf algebroid is defined in terms of a coefficient ring, that's some kind of polynomial algebra in infinitely many variables, and maybe gamma is a polynomial algebra in that. That's something that's relatively easy to adapt because that's the structure of things that are already there. If you want relations in that, then that's where it starts to get a little bit trickier. That's why, I'm not going to say that the R motivic ext is hard. I'm going to admit, maybe not maybe, but I'm very new to C++. So, that's why that's taking a while. And also I just keep not getting back to it. But, some of the things that are different there, it's like, okay, so it does still look like some polynomial algebra over a coefficient ring that's also polynomial. But it's like there's some relations and you have to deal with that. And there's also some issues about degrees with that one where you not only have to specify the Hopf algebroid, but you have to specify a way of truncating it because you need to say, we'll just compute up to a certain point. And the R motivic truncation, again, I'm not going to say it's hard, but it's another issue that comes up when doing this kind of stuff. So, when I say arbitrary Hopf algebroid, like that's true. I think that there are some, maybe I don't want to lean into the word arbitrary too much, but, commonly arbitrary or something. I think you need some kinds of freeness, et cetera. I'm not claiming this as a mathematical theorem in terms of, what kind of generality can you really get here. So I claim that things that you are likely to care about are probably taken care of by this, but depending on how far they are from the examples that Gaussian already has, then, that might involve more or less work, versus just kind of copying and doing trivial modifications to things that are already there. Okay, so that's sort of some comments on how much generality there is. Again, I really only have experience with the examples that I've tried, so I do not claim to be an expert in this program. And, I'm sorry if I've said some things that are not quite right here. Okay, but one of the reasons that this program ended up being really useful to me, especially for the Adamsnovokov computations, is that it gives some amount of multiplicative structure. And I'll say a little bit more about the homological degree 2 elements later, because that's the real magic sauce that makes some of these computations much easier, at least from the math end. But yeah, I sort of see that as equally important as just getting the vector space structure vexed. Okay, so it also does Bochstein spectral sequences, and in terms of what does it output, so you get some text files. So it comes up with its own internal names for elements, and you'll see later on in the talk, I've generated some charts that are labeled in terms of those internal names. The internal names aren't super meaningful, but again, it does additionally have this multiplication feature. So the program will output a text file that says this internal name for an element times, say, beta 1 equals some other possible linear combination of internal names for elements in the resolution. So it outputs text files for multiplications, and for the spectral sequences, say the Bochstein spectral sequences or the algebraic Novokov, that was one of the original motivations here. Again, it outputs a text file that says, in terms of some internal names for the resolution before taking homology, what are the cycles, what are the boundaries, and then I'll say up to some correction terms. And if you want to actually try this out for yourself, a little bit of a shameless plug here. I wrote up some documentation and some charts for the Adamsnovokov case. The documentation should cover most of the examples that are already built in. That's on my GitHub. And I say how to interpret these text files, and I give some Python code that turns the text files into Python objects that you can use in an interactive session. Okay, so now I want to say a little bit about a couple of mathematical or design choices that I thought were notable and interesting and worth mentioning about this. So first is about where the resolutions come from or what they are. So suppose you want to resolve BP star as a BP star BP comodule. The strategy is to first do the version where you've modded out by I. So just as a reminder what these things mean. So recall, so I'll say I is the ideal generated by V0, V1, ... and BP star, which is simply the polynomial algebra on those things. So BP star mod I is at P, BP star BP mod I. So BP star BP is a polynomial algebra over BP star and some generators T1, T2, ... If you mod out by this ideal I, then what you're getting is just a polynomial algebra T1, T2, ... And if you look at what the coproduct is, this is P, the algebra of reduced powers. So P is usually written with generators C1, C2, ... In this discussion, I'll sort of use the T's and the X's interchangeably. So P is the algebra of reduced powers in the Steenrod algebra. And I guess here I'm because I wrote C1, C2, I'm thinking of this at an odd prime, but these are things that work at other primes. You just, well, at other prime, you just have to choose generators differently. So maybe I'll say P greater than 2 here, so I'm not literally lying to you. Okay, so the idea is resolving the mod I versions. So essentially, you have this Hopf algebroid, BP star, BP star, BP, and then you can quotient, and then you get this. Oh, oops, sorry, I'm not supposed to think of it that way, but you can quotient and get this Hopf algebroid FP P. So you're first going to resolve over the smaller one, and then there's going to be an unquotient to get back to a BP star BP resolution. So I'm just giving an example here of what would the first few terms look like, because maybe the first few terms are familiar if you've thought about how to build minimal resolutions for things. So the example here is let's start with the mod I version. So suppose you want to resolve the trivial module over P. So the general version is on the top here. I'm going to be getting a free resolution over P. If the module I'm resolving is trivial, then the first term is just going to be a single copy of P. And then, well, what's the quotient? The quotient is often called P bar. So it's basically everything except the unit. So that's why I'm saying it's the vector space generators are every monomial that isn't just one. And then you want to have that inject into a free P comodule. So the right summands to pick are the primitives. So C1 to the P to the I are the right choices here. And in particular, what this map does is it sends, so for example, so it does the coproduct. So you're going to be sending, say, maybe I'll say C1 to the P plus 1. So that coproduct is going to be C1 bar C1 to the P plus C1 to the P bar C1. And I'm writing it this way to show that I'm getting summands in, or I'm getting terms in each of these things in the minimal resolution. So that's how the minimal resolution works in the FP setting. So in general, so this is what I've got on the right. I'm imagining I've got something from the previous stage, and then I need to figure out what the primitives are and then inject it to that. So this is sort of a standard minimal resolution setup. And the point I want to make is that the strategy taken by Quotient's program is first you do that standard resolution setup mod I, and then if you say, well, actually, I want a resolution over BP star BP, then you're going to lift that resolution that you've got. So, you know, what you're expecting here is if you want to resolve BP star, then the first term looks like BP star BP. The second term, or the quotient there, looks like what happens when you take away the trivial summand, the trivial monomial. And in general, what's going to happen here is suppose MN is the quotient that I've gotten from the previous stage. So that's going to have some generators Yij. And then I'm going to do the coaction. And the idea is these Yijs turn out to be, you can use the same generators as before. except now you're going to do, instead of the previous one, you did the P coaction. This one, you're going to do the BP star BP coaction, which of course has more terms in it, or more terms in it. And the thing you're going to get here is BP star BP on those same YI primitives. So the point is that you can reuse these things. So once you figure out what the summands are supposed to be, you can reuse those summands, but then the map is different. So the map for the second one takes into account the BP star BP coaction. So it's not just, you literally tensor up by BP star. It is different, but the point is that once you've done the mod I minimal resolution, you're kind of halfway there to generating a BP star BP resolution. So this is for efficiency to some extent, I think. Sort of like there's some possible summands in the free thing that you don't have to consider because it's telling you, well, what summands do you need? It's the ones that were generated in the easier computation mod I. A side effect of this is that this program does compute, say, ext over the reduced powers. Okay, so lifting resolutions, I think that's one thing that's interesting about this. The other thing that I want to talk about is the mechanics of taking homology. So this is a very old idea. It's called the Curtis algorithm. Curtis worked a long time ago. The slogan I'm offering here is, how do you take homology? Instead of literally writing out a giant matrix that's mostly zeros, you're going to sort of do a version of that linear algebra calculation, but you're going to represent it as, quote unquote, treat everything as a filtration spectral sequence. So what do I mean by that? So here's a little silly example of maybe you have some spectral sequence and you've identified some generators for the quotients, and maybe you know what the maps do, and you actually have to take homology. So first off, I have these numbered, and the point is that this is some kind of arbitrary ordering. Of generators. So you're going to put an ordering on these generators. It doesn't need to be preserved by the differential. So for example, maybe if I have a copy of BP star in here somewhere, you're going to order the generators of BP star. Lexicographically, if I'm thinking of, maybe I'll say the monomials, thought of as sequences of exponents. So there's no deeper mathematical meaning to this filtration. It's a little bit arbitrary. It's a way of representing generators in a more compact form. So thought of as sequences of exponents. Okay, so that's about the ordering. So suppose we know that this is what our differentials do. So let's see. So the idea is to only pay attention to the leading term. And by leading term, I mean the generator with lowest degree in this arbitrary ordering. So I look at this first differential. So apparently Z1 goes to X2 minus X3. And I'm going to think of that as Z1. Z1 goes to X2, where X2 is now a shorthand for some boundary. And again, okay, so I have 4 things here, so I can show that here we're going to have a non-trivial kernel and image. So I'm going to go down the list for each generator and say, well, what happens? X1 here I'm thinking of this as x1 goes to y1 or some longer linear combination that has leading term y1. So we're just going to represent that internally by the leading term. X2, I'm going to take note of the fact that this is already hit. So again, it's not X2 itself is literally already hit, but this is how we're thinking of these things by abbreviating by their leading terms. Eventually you get in trouble trying to do this. So if you say, you know, X3 hits Y1, and then you're like, well, if we think Y1 has already been hit, then how are we going to take into account, you know, the fact that there's actually other terms going on here? So at this point, you see if something has already been hit, then you add a correction term. So you add a correction term, and then you say, now you make this go to. So I think if you actually work out what to put here, you can cancel out the y1s using x1 and get some multiple of, well, it's going to be some multiple of a linear combination of y2 and y3. But again, we're going with this, just represent everything by the leading term. So we're going to say x3, and we're again, in the internal representation, we're kind of forgetting about these correction terms. So we're going to say x3 hits -2 y2. And again, x4, which really means plus a correction term. You can arrange that correction term such that it goes to 0. So if you kind of squint at this, you know, we've chosen representatives such that this map has an easier form. It sends z1 to x2. It sends x1 to y1, x3 to -2 y2, and x4 to 0. So this is telling us how to choose linear combinations that say are cycles. So you're gonna circle this one and say, okay, we found a cycle, and then you're going to look at the other ones and say, okay, here are relations that are giving us what the differentials are in the spectral sequence. So the Curtis algorithm will produce, you know, up to correction terms, an easily representable or an easily storable representation for what are some cycles and what are some differentials in your spectral sequence. So, you know, this isn't actually doing anything different from the linear algebra that you would have done if you just kind of sat down with the matrix. But it's a convenient way of doing it, and it's sort of one important way that this program works. If you want to learn more about the Curtis algorithm, either because you want to read the code or you know, maybe implement this yourself, there's a great reference with examples that's in Wang and Chu's paper about the algebraic Atiyah-Herzberg spectral sequence. By the way, I can't see the chat when I screen share, so if there's something that I should pay attention to, like maybe somebody can holler.
There was one question from a while ago about whether the Hopf algebroid that the software works with needs to behave well with respect to some prime.
So you can definitely do this at arbitrary primes. So I mean, say like I tried setting up the odd primary Adamsnovokov at arbitrary primes, and I guess sort of, you know, maybe the issues that start coming in are about the truncation. If your prime is too large, then, you know, there's sort of small issues like that, but there is no built-in restriction on the prime. The thing about the Adamsnovokov at p = 2 versus odd primes is that, like, you know, one of them was actually already done, and like small changes needed to be made to make it do odd primes, but there's sort of nothing inherent about the main logic. Okay, and just a few comments about multiplicative structure. So as I'll say in the next part of the talk, when I talk about actually using the output of this for some p = 3 computations, the fact that this computes multiplication not just by homological degree 1 elements, but also by homological degree 2 elements is really, really useful. So I want to point that out, and also just say a couple sentences about how that works. So the point is that there's some Bachstein built in. And I guess when I say homological degree 2 elements, I mean the ones that you're likely to care about anyways, which is if you write out the long exact sequence in ext, BP star to, so I'm looking at the long exact sequence in ext generated by this multiplication by p. So there's a part in the boundary map where as long as your homological degree 2 element is in the image of the boundary map, then this is how this is going to work. So I mean, say if you want to do multiplication by beta elements, this is equivalent to at p equals 2 trying to do multiplication by like hi squared. You're going to end up in this scenario. So the long exact sequence says that the beta elements come from something in ext1 of BP star mod p. So the program works for BP star mod p. So you can compute multiplications. So if I call this thing, like beta bar, so you're going to compute beta bar multiplications in X star of BP star mod p. And then you can essentially do the Bachstein spectral sequence to see what the implications are for multiplication in the integral BP star. So this is a little bit annoying because there are different generators for the BP star mod p version. The program does output a list of translations. So how do the mod p generators correspond to the integral generators? It tells you what the Bachstein spectral sequence does on generators, and it gives you enough information to be able to piece together what are the beta multiplications in the integral X over BP star. So again, I think it requires a little bit of fiddling to go from the text files output by this program to like actually what are the multiplications. And if you check out my GitHub, I've put together a little Python program that does that. Okay, so that's the end of part 1 of my talk. Maybe I'll pause for questions.
I would like to suggest that you put a link to the GitHub data on your home page.
Oh, yeah, I should do that. I haven't updated that in an age. Yeah, thanks for the reminder. All right, so now I want to talk about some Adamsnovokov calculations. So I was interested in this because I wanted to compute the p equals 3 Adamsnovokov spectral sequence, just first to see how far I could get. And then also there's an application to constructing beta families that required knowledge of stems a little bit further than what's been published. So I wondered how much does the computer generated ext tell you in relation to what is the information about the p equals 3 Adamsnovokov that's already known. And the answer turns out to be in the known range. So I'll say I'm thinking of the known range. I believe the most recent calculations that are published are pi less than or equal to 108 of the sphere at p equals 3. is done by Ravenel, and it's in the Green Book. And I wondered how much of that can you reconstruct? So, that calculation is using infinite descent. And I mean, it's pretty involved, I guess. Infinite descent is at least hard for me to get my head around. And it was a fair amount of work. And I wondered if, here you are decades later with this computer data, how much can you get for free just from that? And the answer turns out to be quite a lot. You need a little bit of input to get the first 108 stems, but really quite a lot of it just follows from the multiplicative data. So, oops, yeah, okay. So here this is being glitchy. Okay, here, sorry. I don't know how to make it not do that. Okay. So I have this picture that it isn't great at refreshing the screen, that goes up to 108. This is taken from a picture of this that I have, again, on my GitHub that's colored a little bit differently. But the point is, so it's sort of funny, like usually when you give a research talk, you're trying to say things like, this calculation is really hard, and like, you should be impressed by me and my calculational abilities. And I feel like here the point I want to make is actually kind of the opposite, that like this calculation was like pretty hard and quite a lot of work without computers. And if you use computers, it's not exactly trivial. There are like a couple places where arguments, actual math is needed on top of the computer work, but really almost all of it just kind of comes for free from using both what the E2 page is as a vector space and also this multiplicative information.
So what I wonder is, what happens if you use the computer data and you work really hard?
Yeah, so well, I mean, that was sort of what I wanted to do initially when doing this. And I know I talked to you a bunch about this, and I think eventually I kind of came to the conclusion that you can reproduce the known information without sweating that much. You can definitely go further than that. I think in order for people to really, really care, you would have to go, to maybe 300 or 400. And I don't think these kinds of arguments will get you to 300 or 400. I think you definitely do need something else on top of that, but this is one good tool.
I would say 109 is worth caring about.
Okay, yeah. I mean, I guess I was going to say in terms of care, probably the people in the Zoom room are likely to be the people who would or wouldn't care. But I think at that point I just got pulled off into other projects. I found this beta project that required a detailed calculation in the 144 stem, which is cool because it's something that is much more tractable with this computer data than before. So there was a picture of that I was going to show. I do want to reinforce this point a little bit about like, what exactly do you get from the program and what do you have to input. So maybe I'll say input data you need. So things that I am not claiming to be able to get just from the program. So you need the total differential. So that's kind of uncontroversial. If the point here is going to be to use structure and propagate differentials, you have to start somewhere. So the total differential at p equals 3, it's in the 34 stem. So it's d5 of beta 3/3 is alpha 1 beta 1 cubed. So you have to start with that. So this one I think might be less of a hard requirement, but I tried a little bit, maybe not as extensively, but there are plenty of independent arguments about what happens to beta 7 and beta 9/9. So maybe what I'll write here is what's supposed to happen is that there's a differential, a non-trivial differential on some linear combination of them. And I guess the plus or minus depends on exactly what you mean by those things. And this is like in 106. So, you know, maybe there's a way to get that through other means, but I mean, there's some, you know, pretty accepted, say, like comparison to TMF or something like that, where that one would come from. And the rest in between, I'll say maybe on top of this, I'll put this in another color because it's not things that you actually need other calculations or, you know, other outside information for. So work needed at oh, this is pretty annoying. So it to get the differential computing beta 1 to the 6th. So there's an argument there. It's a total bracket argument. It's not like capital H hard. So I'll give a shout out to Dan who helped me with that one. Differential hitting beta 1 to the 6th. So this is a total bracket argument. And there are a couple more places sort of near the end. So this one here, so this is in the 89 stem. So there's some differential there. And maybe I'll say a couple words about how that goes, because that just kind of highlights why this multiplicative structure is awesome. So you need a D5 in the 89 stem. And essentially, the structure of the argument, and I do have another slide for this, but we'll sort of see what, you know, what seems like a good use of time. So what you're going to say is D5 of beta 2 times the class in the 89 stem. Okay, so you're trying to show that there is a D5 that's non-zero, and so you're going to say suppose not. So suppose that the D5 equals 0. Then D5 of beta 2 times it. So beta 2 is here in the picture, so that's definitely a permanent cycle. Permanent cycle times a permanent cycle is also permanent cycle. So by the way, the D5 is the only possible differential. So ruling saying that the D5 is 0 is the same as saying that it's a permanent cycle. That doesn't really matter in the argument. So essentially, this is a beta 2 multiplication argument. So you're going to say then D5 times beta 2 times this class is 0. And then you actually have, because the program tells you exactly which dots in the spectral sequence this is, you're going to use knowledge of this. So this is going to be a linear combination of other classes. So it turns out to be it's beta 4 times something. So plus beta 3/3 times something else. And the something and the something else are in much lower stems, and those are things that you already know what the differentials are, and then there's essentially it's just this, and you end up with a contradiction. It says that this differential is not 0. So these are the kinds of tricks that you can do if you know multiplication by arbitrary beta elements. So there are a lot of multiples in this. And I actually have a version of this chart that's sort of more for my own use, that's color coded each element based on what divisibilities it has. And, you know, the chart is just like a rainbow of colors. This multiplicative structure really helps with a large number of elements. And so you can just end up finding coincidences like this and then prove differentials that way.
So Eva, John Rognes asks about pi 105.
Oh, yeah.
Zero?
So yeah, actually, I responded to your email this morning. So yeah, that's interesting. So there is apparently a controversy about this, and maybe one thing I'll point out is that in contrast to what's in the Green Book, so the Green Book says that there's two generators in degree 107 modulo the image of J. I think from this chart, it's fairly clear that there's only one. So these things up here, these are high beta multiples. You know, maybe you can see with the colors are supposed to be encoding like just beta propagations of differentials you've seen before. So, you know, the stuff up here is uncontroversial, and essentially it boils down to like there is one dot in that degree. So I think that's yeah, another advertisement for like using computers to do this, because, you know, both of the conflicting methods that disagreed about that stem were pretty hard, versus this, you just look at a picture and you're like, oh, there's one dot. So
that was kind of about pi 107, I think. 105, it looks like there's like a brown and a red.
Okay, yeah. So that one is a little bit less of a win for this. So there was a question about like exactly what element goes here. So what I can say here is of these two dots, so it like this is kind of a limitation of this, where like it tells you what dots are where and how to multiply them, but it's not always clear how to connect them to well-known classes. So I know that this thing, I don't know if you can read the labels, but say the lower dot in the 81 stem is alpha 1, whoops, sorry. The lower one is, I think it's just called X81, but the point is that it's a alpha X, sorry, let me look at a place where I remembered what this does. Oh, I know. Oh, okay. It's alpha beta 5. So this one I can confirm because it's the one such that alpha times it should be beta times beta 1 times beta 5. So this one I can identify. There's also supposed to be gamma 2 in the stem. And this is, I think, a limitation of me and not anything else, that I don't know whether gamma 2 is, you know, which linear combinations of the dots is it? Is it actually the thing that's labeled as the other dot, or is it the other dot plus alpha beta 5? And the answer to that question determines, so I actually, well, here's the other problem, is that a lot of these arguments, you can show that differentials are non-zero. Or you can even show, like, say, I know that this differential hits the first, like, neither of the coefficients are zero. It's either the first class plus the second class or the first class minus the second class. So I do kind of know what this hits. And what I think what I'm going to say here is that what's left here is either alpha 1 beta 1 squared gamma 2, or this plus the other class. And that ambiguity would be resolved if I knew more about gamma 2. So maybe that's something for me to think about.
But still, that doesn't, about pi 105, it looks like you're claiming that pi 105, at least at the prime 3, is 0. And this uncertainty about the target of that differential doesn't change that, doesn't affect that.
So I
conclusion on pi
I don't think there was a controversy about whether pi 105 was 0. I think there's a controversy about what the target is, and then that was linked to a controversy about the rank of 107. So I think I've addressed both of those issues.
Okay, thanks.
Yeah, I was just going to say, we used in the book with Bob, we used the vanishing of pi 105 to construct a certain total bracket. So I just wanted to know that that was still safe. I wasn't really getting into the actual ambiguity.
Oh,
Yeah,
okay.
thanks.
Yeah, I guess I believe. Well, okay. So maybe what I'll say about that is this red differential here. That was one of the ones I said that I used, like, quote unquote common knowledge, that beta 7 and beta 9/9 support a differential to the first thing. I guess the thing that does require the argument that the multiplicative argument that I was talking about is the fact that the class that I'm circling right now is hit. And, like, yeah, I guess I'm claiming that class is hit and that 105 is 0. I'm not aware of anybody claiming that 105 is non-zero. Okay, I guess I'm over time. Maybe there's just one point that I wanted to make in the next slide. Oh, that's not what I wanted. So here is the region to the right of the region I was showing before. There are two things colored in. So this line is, this is just sort of empirically using the multiplicative data in the program. So everything above this line is beta 1 divisible. And then the shaded region is, so the setup for this, why did I pick this portion? I have some calculation where you need to know what's going on in the 144 stem. So in particular, I was interested in the 144 stem for the sphere mod 3 and V1 to the 9th. And okay, so that is sort of a ways past, the information, the work that I was talking about that goes up to 108. There are some differentials in low stems that I haven't worked out yet along the way. So I'm not claiming that I know everything from 108 to 144, but I was able to get the answers that I wanted in 144. And a large part of the reason is everything in the shaded region is a beta 1 multiple, or beta 1 to some power multiple of a class in degree in stem less than or equal to 108. So the point is, okay, what's going on in 108, either because I claim I can independently calculate that. Oh yeah, I guess for completeness, there was one thing I should say. So there was an argument needed in 89. There's an argument needed in 105. And that's another one of these multiplicative things. And that's it. So at any rate, either because I claim I can independently calculate up to 108, or because previous sources have calculated up to 108. You kind of know what's going on in the shaded region, and that's like most of it. And then that plus the fact that the shortest possible differential is a D5. It's not like there's no room for things that you didn't know about before, but that drastically cuts down on the things, where interesting behavior or previously unknown behavior could happen. And I'm also going to say, I would love it if somebody could say something about, like, there seems to be a largish region where everything is beta 1 divisible. And I tried a little bit using some techniques in Palmieri's book to come up with a beta 1 divisibility region, and it's just nowhere close to optimal. So, you know, at this point, the program is doing great things by, you know, giving a much bigger beta 1 divisibility region than the one that I know how to prove. Maybe somebody will come along and prove a better one, because I think there's room for that. But then, you know, maybe the program will help give some sense of what the optimal answer should be. Yeah, I think that's most of what I wanted to hit. Maybe I'll stop now.
Okay, let's thank her. And if there are questions, people can feel free to unmute and fire away. All right, if not, then
Maybe I
go
can
ahead.
ask, is your application in 144, is this about identifying the Rebich image from the sphere in TMF at three,
Yeah.
or is it?
Yeah, it is. So it shows that V2 to the 9th is a permanent cycle mod 3 and V1 to the 9th. And that gets you some new beta families.
Did Mark Behrens know that a long time ago? Wasn't his thesis about something like that?
So Mark Behrens and Satya Pimaraju have a paper about V2 to the 9th mod 3 and V1. And that gets you some beta families, but not all of the beta families needed for TMF. So I think this image of TMF thing, to me, it seems like people in the know sort of quote unquote knew this, but I'm, you know, because the mod V1 paper isn't enough to actually recover all the necessary families, I don't think anybody, so I guess, for that, so I should mention, so Shimamura is my co-author on that. This was kind of one of those co-authorship situations where both people did the same thing. Shimamura had a preprint about this a while ago. Maybe there were some issues about the preprint, and then we sort of collaborated and wrote this paper that incorporated some computer calculations and also some of his ideas. Other than that, it did sort of seem like one of these things where like everybody quote unquote knew it, but then there wasn't at least a published proof in the literature.
Are you his first non-Japanese co-author?
People have told me that. I guess I didn't actually bother to look it up, but I think that's probably true, yeah.
Great. I'm glad you did that.
Other questions? All right, let's thank Eva one more time.